Yeah, roughly 50 minutes, and then you can go a little bit over time if necessary, and then wish questions.
Yeah, okay. So 50 minutes anyway, yeah.
Yeah.
Good.
Yeah. Yeah, that's be good. So, okay. Yeah, so before we, I'll play the anthem, Bruce.
Okay, lovely, thank you.
When I think it's like more time.
You can start it, yeah.
Yeah. Just a minute.
This is like the World Cup, right? With Morocco winning yesterday.
We are winning. Africa is winning this one.
Yeah.
Yes, we are winning. This is the World Cup for Africa. We are winning this one. I can tell. Let's see.
And ER is in Mozambique, so Portugal winning yesterday. I don't know how that went down.
Yeah. So they were for her it was double celebration.
Yeah, of course there's a connection, and the language is the same, and the culture.
It's the same even for us when England wins. We are still a queen's country, even though they have a king now. So sorry, I want to stop this. Let me play the anthem and then we can start.
Africa, sing now, Africa, sing loud, sing to the people. We'll ring the bells when you come back. We'll beat the drums when you come back. We'll ring the bells when you come back. We'll beat the drums when you come back. Our lost African music will turn into the music of the people. Here's the people's music, but the people's culture, and I'll be the one who'll climb up the mountain, reaching for the top of our Africa days. Africa sing, Africa sing, Africa sing, Africa sing, sing, sing Africa, sing, sing Africa, sing, sing Africa, sing, sing Africa. My boo, yeah, Africa.
Lovely. Yes, that's such a lovely song, and welcome everybody to the African Mathematics Seminar today. I have the pleasure to introduce the speaker, Simon Willerton from Sheffield University. So Simon was actually my PhD advisor, so it's a great pleasure for me to introduce him. He's been to Africa once before. Sheffield has an arrangement with the University of Nairobi for dealing with teaching large classes. So I think that's great, and I'd like to learn more about that actually myself. And as the song goes, we'll ring the bells when you come back, and so we'd like to get you back to Africa, Simon. And I hope to get you to visit South Africa in the near future. Yeah. And Simon is a mathematician with many research interests. He has the distinction of having one paper roughly in just about every archive section on the mathematics archive, which is quite remarkable. His work is characterized, I would say, in using the word elegance in both on the research side and on the teaching side, as I think we'll see today. And if there's any postgrads out there that are interested, I'm sure, and you possible postgrads, give him an email afterwards if you find his way of thinking about maths as attractive as I do. But anyway, Simon, we look forward to your talk.
Thanks, Bruce. Can you hear me okay?
Yes.
Great. Okay. So yeah, I'm not sure I can quite live up to that fantastic introduction, and yeah, and the fantastic opening music as well. Yeah. So thank you very much for the opportunity to speak at this seminar. Yeah, as Bruce said, I've only been to Kenya. That's the only time I've been to Africa. It's shocking I've not been to South Africa yet, but hopefully we can correct that. But when I was visiting Jared, you know, he sent us off on a safari, and so maybe the talk today is going to be a bit of a safari. We'll see. I mean, I wasn't really sure of the audience, so I've given quite a bit of a broad talk. So we'll have a little bit of a sort of a drive out. So that will be the sort of the first section on sort of the category theory bit of things. But then once we sort of get where we're going, we'll go and see a few kind of interesting animals along the way. So as Bruce maybe hinted, the sorts of various things that will crop up from different areas of maths. So I hope it's not too broad, or well, we'll see. So I'll just dive in. So as the title suggests, you know, we're going to be thinking about metric spaces as enriched categories. And as I sort of said in the abstract, I wasn't going to assume too much in the way of category theory. So I know it's a pure maths audience, but I'm not really sure what that means. But anyway, let me find the right screen. So just a little bit of enriched category theory to start with. Oops, I thought I'd started my timer. I haven't started my timer. Right. So in category theory, you know, there's a notion of a category, but the notion of a category, you know, is quite encompassing. So there's sort of various kinds of categories that get considered. So on the one hand, I made this distinction here between sort of large categories and small categories. Now that's in inverted commas because that's not in any sort of technical sense of the words large and small. So maybe a better sense would have been sort of categories of structure and then categories as things in their own right, as in objects in their own interest. Anyway, let me just say what I mean. So when you're first starting thinking about categories, you get told that lots of things you study in lots of things you've studied in maths actually fit into categories. So you have things like objects, which are often maybe structured sets, and maps between them which preserve structure in some way. So you might look at, say, vector spaces. Let me just get rid of that off my screen. So you might look at, for instance, vector spaces and linear maps between them, or sets and functions, abelian groups, and group homomorphisms, or I'll come to this a bit more in a second. The representation category of let's say an algebra or a group or something like that. So you'll have the representations as the objects in the category, and let's say the intertwiners, the maps between them which preserve the action as the morphisms. And so there are sort of algebraic examples, but you also get sort of topological examples, or in other bits of maths, so category of topological spaces and continuous maps, or semi-simplicial sets, if you know what they are. So, and you know, category theory arose as sort of a bridge between algebra and topology, or algebra and geometry, and so it was about creating functors sort of initially between, say, topological spaces and algebraic things. So you're getting algebraic invariant. So that's the kind of thing you were thinking of. So that's sort of where its origins were, and it was taken by algebraic geometers in various other areas. But as well as those sorts of big structural categories, there's these sort of categories arise as sort of structures in their own right. So for instance, if you have a group, then you can consider that as a category. So it's which sometimes called BG. So that's a one object category, which I just represent by that red dot there, and the morphisms from that one object to itself is just the group, and the composition in the category is just a multiplication in the group. Okay, so that's a lot smaller in many senses than those sort of categories of structure that are considered at the top. And similarly, an algebra. So by algebra, I guess, if you don't know what an algebra is, I'm just thinking of a vector space over the complex numbers with a product on it. So the group algebra of a finite group or something. So in particular, an algebra is a vector space. And for simplicity, like I say, I'll work over the complex numbers, but that doesn't really matter. And so that's a vector space with a product on it. And we can consider that as a one object category as well, where we just have again, the algebra there is just being thought of as the morphisms from one object to itself, and the product in the algebra is given as the composition. So there are two examples. So another kind of structure that can be viewed as a category itself is a poset. So if you've got a poset, say indicated here, we've got some elements and some relations between the elements. So we can consider that as a category where we have a morphism from an element P to an element Q, if and only if P is less than or equal to Q. Or we could have, there's a decision there about convention. We could have said if P is greater than or equal to Q. But that gives us a category whose objects are the elements of the poset. And this is sort of at the other extreme to the group case. Though we only had one object and lots of morphisms, in this case we have lots of objects, but at most one morphism between each object. And then another example from topology, if you've got a topological space, then you might consider the poset of open sets. So that's just an example of that. So we've got these sort of big categories of structure, and then sort of these other categories where we're thinking of them as things in their own right. I mean, that's probably, it's not an exclusive dichotomy. Things will probably fall between those two sort of camps. But anyway, so given categories C and D, we can form a product category. So the objects are just the product of the objects in C and D. And we can also form a functor category. So given a category C and a category D, we can look at all of the functors from C to D, and that gives us the objects. And the morphisms are going to be, so a morphism from F to G will be a natural transformation between them. So then between each pair of morphisms, we have a set of natural transformations, and that gives us a category. So I wrote that with these square brackets, but sometimes it's written in this sort of notation, C to D. Okay. So do shout out if anyone has any questions. Okay. So in particular, when we're doing category theory, there's this special role given to the category of sets, because sets are everywhere in category theory. So, between each pair of objects, I mean, if we're in a locally small category at least, you have a set of morphisms, and the and composition is a function in a certain way, etc. So set has a sort of special role, and the category of sort of scalar valued functions, given a category C, you can get very interested in the functors into the category of sets. You can either look at the functors or the contravariant functors. So this means the functors from the opposite category. So we're just switching around what goes on. And so what category theorists sort of make this quite scary, because they call these things pre-sheaves or co-pre-sheaves. So they'll talk about the category of pre-sheaf. So you think this has got to do with sheaf theory, but no, it's just like, if you have down at the bottom here, I say, if you've got a set, you often consider the scalar valued functions on that set. And that's sort of really what this is the analog of. So this is just like looking at the scalar valued functions on a set. This is the scalar valued functors, where we're thinking of the category of sets as the sort of category of scalars. So this is a sort of fundamental object, which is given a kind of scary name for no good reason, I don't think. But if we sort of think of an example, so if we have a group and we look at this one object category BG, and we look at the functors into set, then this gives us, well, associated, so we've got one object in our category, and we're mapping it to the category of set. So we're picking out a single set, and then each element in the group gives us a function from that set to itself. So we get an action of the group on the category. So on that set. So each functor from BG into set gives you an action of G on a set, and then you work out what the natural transformations are and between two functors, and that turns out to be an intertwiner between the corresponding actions. So this scalar valued functors or presheaves is just a category of left G actions and intertwiners. And similarly, if we look at the contravariant functors, so we switch around the way we're composing the elements in G, then that gives us the right action. So that's just what's going on there. And if we had a topological space and we looked at this category of open sets, then this fundamental thing, this scalar valued functors on the category of open sets, or well, with the arrows reversed, is the sort of classical notion of presheaves on your topological space. So that's where the name comes from. But in general, I mean, these objects don't really have much to do with presheaves, but this is where the name comes from. Okay, and so the sort of big result in category theory says that you can faithfully embed your category into its category of scalar valued functors. So as I've written here, so you should think about embedding a set in its category of into its algebra or monoid of functions, or just a set of functions, integer valued functions on that, just by mapping an element of the set to the delta function, just the function that spits out 1 at that point. And so yeah, the Uneda lemma says that you can faithfully embed the category inside there. Okay, I don't want to say too much about that, other than give you an example here, which is Cayley's theorem, which is, if we apply this for our group, it's saying that the group sort of, if we look what this does, what this embedded, it sends the one object category thought of as with G as its automorphisms there, it maps it to the set G, the underlying set of G, with the action of G by the left action. And so the fact that this is a faithful embedding says that G is acting faithfully on itself. So it's saying that G embeds in a permutation group, and indeed that is precisely as Cayley's theorem. So Uneda lemma is just an example of sort of Cayley's theorem about every finite group being a permutation group. It's a sort of I mean, we'll see more examples of it later, but this is a sort of fundamental thing. Okay, so the idea was that this is a fundamental category, so analogous to the functions on a set or something. Okay, so moving on then, it's not always correct to use set as the scalars. So for instance, I talked about an algebra, just an algebra over the complex numbers, say. Then we've got the representation category of A. So that's A acting on complex vector spaces. In this case, I mean, we've got two things. So here we got the action category was just the functors from BG into the category of sets. But here we can't just recover that for an algebra A and the representation category. We'd like to say that it's the functors from this one object category with A as its morphisms into the category of vector spaces. So each functor will just pick out a vector space and give you an action on that. But the point is that you need to remember the vector space structure. And if you're just thinking about these as functors, then you're not going to do that. If you're just thinking about sets there. So the category of representations is in some sense a linear functors. So and moreover, I mean, both A and the category of representations of A have this sort of vector space structure inside them. If you're just thinking of them as categories, then you don't see that vector space structure. You just see the Hom set, which is just your algebra A. You don't see, well, you see the product in it because of the composition, but you don't see the vector space structure. So the idea is that you want to do category theory over a different base category to the category of sets. Okay, so many circumstances, yeah, so it's better to use something other than the category of sets. And the idea is that you need the right thing to have, in fact, is a monoidal category. So we have a category V, but we want it to have some tensor product on it and a unit for the tensor product. So we have a category, some way of multiplying the category by itself, and a unit for that inside the set of objects. So the example, the basic example is the category of sets with the Cartesian product. You can, given two sets, you can form their Cartesian product, that's another set. And the one object set, the one element set, is the unit object for that. If you take the product with a one object set, then that's isomorphic to your original element, your original set. Or the one we're interested in this discussion above here is the category of vector spaces. So given two vector spaces, you can form the tensor product of those. And if we're working over complex numbers, then the vector space of complex numbers is the unit object. They're tensoring any vector space with the complex numbers just gives you the same vector space back. But we've got another category which I'm going to be really interested in, which is the category here, which I call R plus bar. And the objects of the category are the numbers from 0 to infinity, including 0 infinity, so the extended non-negative reals, and with greater than equal to, thinking of a poset. So what this means, so I've drawn the non-negative real numbers pointing upwards, and my morphisms come down. So I've got a morphism from B to A if B is above A. If B is bigger than A, then I get a morphism. Oh, and I've drawn that the wrong way around here, so that's a typo. That should be B to A. So that gives me that's a poset, so that gives me a category with the arrows as I've shown, and I get a monoidal structure on there, so just by addition. So I can add numbers together, and that gives me the kind of structure I want in the category. And of course, adding 0 to anything doesn't change it, so that's my unit in there. Okay, so these are three examples of monoidal categories, and I want to define a notion of categories with doing categories using those monoidal categories as a basis. So normal category, so we have a collection of objects, and for every pair of objects we get, so I'm using category theorist notation here, so this is the Hom set from X to Y, and that's a set, which is an object in the category of sets. And then for every triple X, Y, and Z, I have a composition, which gives us a way of composing something from X to Y and something from Y to Z to give me something from X to Z. And this is using the Cartesian product of sets, and this is a function of sets. And then I've got an identity for every element X. I have the identity morphism inside the set of morphisms from X to X. Okay, and I can think of having something inside a set is the same as having a morphism from a one element set into that set. Okay, so I can rewrite this condition here as having something from the one element set into for every X into the set of morphism from X to X that picks out the identity arrow, and that satisfies some axioms which I won't bother about. Now, if I'm changing the basis, if I'm talking about V enriched category, so here where V is typically either the vector spaces or set, or we'll go on to these non-negative reals. So again, I've got a collection of objects, and for every X and Y, I don't have a set now, but I have an object of my category. So if I was taking vec, this would be a vector space rather than a set. And for every triple, I have the object from X to Y, the object of things from Y to Z, and I use the tensor product in V. So this would be a morphism from, if I'm using vect, the tensor product of the vector spaces into the vector space. And so that would give us a bilinear map in that case. And then for every x, we get a morphism from the unit object in V into the object from x to x. And the idea is, if that's vect, then that's a morphism from a linear map from the complex numbers into my vector space. So that's just again picking out an element, and that satisfies some axioms. And then we have a notion of a V functor, which gives for just a function on the objects, just like an ordinary functor, and for each pair of elements in the category, it gives us a morphism in V from the V object from X to Y to the image of it over in D. Okay, but so that's in V. So if you're taking vector spaces, that would be a linear map there. Okay, so if V is nice, then V is also a V you can give it as a structure of a V category. So for vector spaces are nice. The morphisms from one vector space to another, the set of morphisms form a vector space themselves, and that's what we mean by nice in that case. And if it's nice in other ways, then we can always also make the functor category, the collection of functors from one V category into another, into a V category. So in this way, if we've got an algebra, we think of that as a vect enriched category, because it is just an algebra is a vector space with a product, and if we look at these linear functors into the category of vector spaces, then we get exactly the representation category. So working over vect rather than set gives us often the things we want to do in representation theory. But I want to do something completely different here. I want to work with R plus bar. So this is this category here where the objects are non-negative real numbers. Okay. So in this case, what happens when we take this definition? So now we get a collection of objects. Now for every pair of objects, we get not a set, but a number. Okay, so that's the first weird thing. We don't have a set of arrows from X to Y, we just have a number, okay, which is a bit bizarre, but let's bear with it. And then for every triple, our composition axiom says that because an arrow in the category R plus bar is just saying something is bigger than or equal to something else, and our monoidal product is addition, it's just saying that the number from X to Y plus the number from Y to Z is bigger than or equal to the number from X to Z. So that's just a triangle inequality, of course. And then our identity axiom says that 0 is bigger than the number from X to X. But the number was non-negative, so that's just another way of saying that the number from X to X is 0. And it turns out that there's no additional, the other axioms are trivial. So this is what doing category theory over this category of non-negative real numbers is. So this is, hopefully you've spotted, this is sort of a generalization of a metric space. So for each object, pair of objects, we've got a number between them from X to Y, and it satisfies the triangle inequality, and you've got 0 self-distance. But this is more general than a metric space, because it's not necessarily symmetric, for instance, and so the distance from X to Y is not necessarily the same as the distance from Y to X. That's not in these axioms at all. We can have infinity as a distance, so that's not in your sort of standard notion of a metric space. You don't tend to allow infinity as a distance. And we also have that the distance from X to Y being 0 does not necessarily imply that X is equal to Y. We'll see an example of that. We'll see a couple of good examples of that in a second. So we have this notion which just naturally crops up in category theory of this generalized notion of metric space. And so we can consider a metric space as being a kind of category, just as we can consider a group or a poset as being a kind of category, but in this sort of in this enriched case. So we can do category theory with these things. Now, in particular, we've got the notion of a functor between R plus bar categories, And if you check out what my definition here was, it's just going to be a function between the underlying sets, and we're going to have some inequality because we've got a morphism there. So it's just saying that this we've got morphism, a function between the underlying sets, and what happens. So here, you know, this is what would normally be written D. I'm just using the category theorist notation here. So x of x comma x primes means the distance from x to x primed in this case. So it's saying the distance from x to x primed is greater than or equal to the distance between their images. So it's a Lipschitz one map, or it's a distance non-increasing map, or for short, we just call it a short map. Okay, so that's what the category theory tells us the sensible notion of morphism is there. So let me give you some examples of these things. So as I said, in nice cases, you want the enriching category itself to be a category enriched over itself. So what is the right metric to put on the non-negative real numbers? Well, it turns out it's this one. Okay, so it's very asymmetric. So let's go back to my picture here. So we've got the non-negative real numbers have got 0 at the bottom going upwards, and the idea is that if I'm going upwards, then it costs me the distance that I have to go, but it's free to come down. So it's no distance to come downwards. I can just drop with gravity, but I have do a bit of work to go upwards. So the distance here from A to B is the maximum of B minus A and 0. So it's always a positive number. And another way to write that is this sort of so-called truncated difference. So that's just defining what this is. B minus dot of A is just B minus A if that's positive, and 0 if it's negative. Okay. Right. Okay. So then we have the category, this sort of enriched category of functors from x to y. So x to y here are enriched metric spaces. Sorry, these generalized metric spaces. So we want to put a generalized metric space structure on the functions from x to y, these short maps from x to y. So what is the distance from f to g? If f and g are going from big X to big Y, well, we just look for each point in X, we just look where F and G send it, and we look at the distance from F of X to G of X, and we look at the worst or the biggest it moves that difference is. So we just take the sum. So it's just measuring how far apart those maps are. What's the furthest those maps are apart. Okay, and that turns out to give us one of these generalized metrics, so it will satisfy the triangle inequality, etc. Now, if we look at this sort of scalar valued function, so these are just real valued short maps. So here so we're taking values in the reals, and so we're just looking at the difference between the values that the functions take. And you know, if you've ever done real analysis and you're looking at functions on the real line, say the interval from 0 to 1, you look at real valued functions, then this is a symmetrized version of that is what you consider in that case. Okay, so then we've got the Yaneda lemma, which said that, if you remember, it said that X, any enriched category, embeds in, well, I didn't tell you that Yaneda also works for enriched category theory. So we've got that any enriched category embeds into its scalar valued functors. So embeds faithfully. So what that's saying is that if we look at these real valued functions on X, then we've got an isometric embedding of the original metric space into its functions with this metric on it, and that's called that's sort of a generalization of the so-called Kuratowski embedding theorem. So a point X gets sent to the function which sends a point to the distance to X. Okay, so that sort of ties this in with sort of a bit of classical metric space theory. And then here's another example of one of these generalized metric spaces where it's asymmetric. So if we start, even if you just start with a classical metric space, a symmetric thing, why you might be interested in these more general ones. So we can form a category. So the objects of this category, we're going to form this enriched category. So this is this metric space. So we take all the compact subsets of M. So here's our M, and here's two compact subsets A and B. And we're going to say the distance from A to B is, we look at a point in A, and we look at the shortest distance to B. We find the point in B which is nearest, and we take that as the distance from little a to big B, and then we work out the worst that can happen in A. So we take this expression here involving subs and ints, but basically if you're in A, if you pick a random point in A, what's the furthest you're going to have to go to get to B? And that turns out to be one of these generalized metric spaces. So and what we have, so if you're observant, you'll notice that the difference from A to B, big A to B, is 0 precisely when A is a subset. So if you're in A, which is a subset of B, then it's going to take you no distance to get into B. And so this is sort of a generalization, or a sort of a refinement of the usual Hausdorff metric, but this contains more information, and you get the Hausdorff metric by sort of symmetrizing between A and B, which is sort of a kind of very drastic thing to do. Okay, so sort of illustrated there some examples of these asymmetric metric spaces, these generalized metric spaces, and why these are sort of natural. So we've seen this is a natural thing that comes up in category theory, and it's a sort of a natural generalization of metric spaces. So that's sort of cool in itself, but I just want to, now we've done that, I really want to kind of change gears a little and just give you a few examples of where these have been used, or where this has come up. So the category theory is going to drop back for a second now, and we're going to see various other things cropping up. So I'm going to talk about magnitude. So magnitude generalizes the notion of Euler characteristic. Okay, so Euler characteristic you might have come across for topological spaces and things, but turns out Euler characteristic crops up in various bits of maths. So for instance, for finite sets, I mean, the cardinality of a finite set is the right notion of, is the thing that Euler characteristic generalizes, you could say. But Terry Wall came up with the notion of a correct notion of Euler characteristic for finite groups. So if you've got a finite group, then the idea is you take the reciprocal of its cardinality, and that's the right notion of Euler characteristic. I'm not telling you why it's the right notion, but just believe me on this. And similarly for finite posets, Rota gave this definition of an Euler characteristic for finite posets, which was the sort of right one. Now these are all examples of finite categories. We've seen that finite groups and finite posets are examples of finite categories. And finite sets, well, you just take the category with no morphisms in it. That gives you a finite category. So Tom Leinster sort of realized that he could generalize all of these into a single notion of Euler characteristic if we've got a finite category. It's a sort of complicated definition, or a non-obvious definition, not terribly complicated, but it's not intuitive. So I'm not going to, I won't tell you what it is. But then he noticed that we can actually work in the world of enriched categories. So if we have one of these enriching categories, V, and it's got a little bit of structure called a size on it, then we can define an Euler characteristic there. And of course, finite metric spaces are examples of these things, where we're taking V to be these non-negative real numbers. So you realize, well, okay, so I can just define this notion of Euler characteristic for finite metric spaces. Now, at that point, we thought that Euler characteristic was a far too confusing name, because for what's an Euler characteristic of a metric space. So we decided to so Tom and I got the thesaurus out and looked up lots of words, and we settled for magnitude. So the magnitude of a finite metric space sort of comes from thinking about the category theory and these notions of Euler characteristic from other bits of maths. Okay, and it turns out this has some remarkable properties, or lots of interesting stuff. So, and I'm going to kind of whiz through these a little bit. So if we have a finite metric space, we're going to talk about the notion of weighting. So this is just a real valued function on the metric space satisfying this property. So if we think of all of us, separated around the globe as we are, and a weighting is going to be assigning a number to each of us, such that if I think about me, if I add the exponential of the distance to each of you multiplied by your weighting, I want it to add up to 1. So I want, if that's telling how much love you've got for me, which can be negative note, then I want, and this decays exponentially with distance, then I want the total love that I'm feeling, even if there's people who are really not loving me at this moment because they've seen far too much category theory. I want that to total 1 that I'm sensing. And similarly for Jared and Bruce and everyone else, experiences for each of us, when we sum this weighted exponential of the distance, we get 1. And it's a sort of bizarre thing to want to do, but let's do it. And if a weighting exists, which it might not do, we define the magnitude of our finite metric space just to be the sum of the weighting. So let's just do that, and that gives us a number. And so, for instance, if we have a sort of a finite metric space like this 3-point space here, we might take, the idea is that these 2 points are, I've got that there. Yeah, no, that's the right way around. So these 2 points are very close together. So you might, and these two are very far apart. I mean, if t was 1,000 here, then you might take a weighting of close to a half for these 2 points because they're very close and they're supporting each other, and a weighting of close to 1 at this point here. Then we add them up, then we're going to get something close to 2. Okay. And it turns out that it's interesting to consider what happens if we scale the metric space. So t times x is the metric space scaled up by a factor of t. So we get a function associated to t, and let's see what happens for this metric space here. So if the points are all really close together, then we may as well put like a third weighting on each of the points, because they're really experiencing the weighting to full effect. So the distance is nearly 0, then this exponential is nearly 1, and so we can just put a third weighting on each of these points. So we add it all together and we get something close to 1. Okay, so this picture, let me just say a little bit more about this bit. This picture is not quite to scale. The idea is that I've got, these, sorry, I realise you should have shouted at me if didn't notice I'm on my slides there. So if these points are really, so we've got 1 point really far apart and 2 points really close together. Now, if they're all really close together, we can have a third. Now, as we move them apart a bit, then I'll probably want a weighting of 1 on this point and, sorry, got the reflection the other way around. Right, yeah. So I've got sort of weighting of like a half on each of those points and 1 on that point. And so the total magnitude is 1 in that case. And then now, if I make t really, really big, so all 3 points are really, really far apart, then they're going to need a weighting of close to 1 on each, because they really don't feel the weighting from each other. So then in that case, the magnitude is roughly 3. So if we plot the magnitude against t, then we see something close to this graph, which is it's kind of telling you the effective number of points in this case. So if they're all really close together, there's effectively 1 point. If they're slightly spread out, then you can't distinguish those 2 points from this point, so those 2 points from each other, sorry, but you can distinguish in that point. So it looks like there's sort of 2 points, which is in this region here. And when they're all really far apart, we see that there's actually 3 points. And as t tends to infinity, the magnitude will tend to the number of points in the finite metric space. Okay. So this is just this generalization of Euler characteristic. This is what it gives you when you look at metric spaces. Okay, now it turns out, this is an interesting thing to look at. So it turns out, as we'll see, to have various connections to other things. So here's an example. So if we've got an ecosystem, so here we're going on safari, and in our ecosystem, we're going to think of that as a selection of species, which might be a cheetah, lion, an elephant, and a giraffe, say. And we think we want to see how diverse this ecosystem is. So we're going to use some measure of difference between the species. So here, a cheetah and a lion might be thought of as being quite similar. So they don't add, having two of those doesn't add too much to the diversity of the ecosystem. But the other species are maybe quite different to each other. So if we model our ecosystem like this, so we just have a point for each species and a notion of distance between them, we get a finite metric space, and we can take the magnitude. And it turns out that this is a sensible measure of biodiversity. And in fact, this was looked at, long before, back in 1994 by two ecologists. They came up with this notion, which turns out to be essentially the same as magnitude, but they were looking specifically at ecosystems, not at general metric spaces. And that's a kind of sensible thing to do. So Solov and Pulaski actually thought about this before the notion of magnitude existed. Now, but it turns out that the connection goes deeper than that. So this is what Tom Leinster sort of was led to look at. He sort of thought about what else do you look at in terms of diversity. Well, traditional diversity measures don't just use what species you've got, but also the number of the relative proportions of species, and so you can think of that as being like a probability measure. So you might have like a quarter cheetahs, an 8 lions, a half elephants, and whatever left for giraffes. So in your ecosystem, that's the distribution. So traditionally, people just use the relative proportions, they don't use the difference, but Tom and the measures they use are kind of connected to notions of entropy. And Tom was able to sort of use that to come up with a sort of, together with Christine Cobbold, combine these two approaches to give a new diversity measure which used both relative proportions of species and differences of species. And the magnitude tells you something about that, so the old-fashioned magnitude. But this measure, as it says here, so I just picked the title of a paper from Fungal Ecology. So this stuff coming from this enriched category theory does improve inferences about microbial diversity. So using these structures. Okay, so we've got onto sort of biological diversity by thinking about enriched categories, and then we've got other structures coming up here. So in knot theory, there's something called the Jones polynomial, which is a polynomial, and that can be categorified. So it turns out there's a homology theory which you can associate to knots and links, so that when it's a bigraded homology theory. I'm gonna speak quite quickly now, so don't worry if you don't understand much of the concept here. That's fine. But we get a bigraded homology theory, and it turns out that if you take the Euler characteristic of that in a certain way, that gives you the Jones polynomial back. And this homology theory of links has a lot more structure. It has functoriality than the Jones polynomial. Turns out there's a similar categorification of magnitude. So if we just take a simple example of graphs, because that's easier to explain. So we think of a finite graph as a metric space where we just take the shortest path metric on here. So I've just taken the cyclic graph here. So the distance from one point to another, you just take the shortest path. So we can think of that as a finite metric space. And so given we can use the magnitude, so we take our graph, we scale it up by a factor of t, that gives us a function of t. But if we think of that as a function of q, which is e to the minus t, we make that substitution. It turns out that for graphs, we always get a power series. So here we have this power series associated to the cyclic graph, which starts 5 minus 10q plus 10q squared, etc., etc. That goes on. So it turns out that there's a bigraded homology theory of graphs whose Euler characteristic gives you back the magnitude in this sense. Okay? So there's this sort of this richer structure sitting above magnitude. So the Euler characteristic of that is just the magnitude. Now let me just give you an example here. So we've got this bigraded homology theory. So for each k and l, we get some abelian group, and here's just the ranks of these abelian groups for some k's and l's. And I'm just saying that the Euler, the level-wise Euler characteristic of this gives you these coefficients here. So we've got 5 gives you 5, then minus 10, and then plus 10, and then we get 0 for level 3 because we've got no cubic coefficient. Then we've got 30 minus 10 gives you 20, 50 minus 10 gives you 40, 20 minus 70 plus 10 gives you 40, etc. So it turns out there's this much richer structure. Now I've given this example just for graphs, but you can state this in a more complicated way that Tom Leinster and Mike Schulman showed. You can actually do this for metric spaces in general. Okay? So there's a more rich homology theory, so not just associating a number to a metric space, but you get these you get a homology theory. Okay. And that works in more generally in the enriched category setting as well. It's not just about metric spaces. Okay. Now, it turns out you can do, again, I'll go quite fast through this. So we've just been looking at finite metric spaces, but you can actually do this for infinite metric spaces as well. So here's an example. So if we just take length little l, and we can look at n points in a line, sort of giving total distance out. As we let n get bigger and bigger and bigger, then it's kind of filling up the interval from just the length little l interval there. So we're getting closer and closer just to the length l interval, if you like. But it turns out that the magnitude of those finite sets actually converges. So it converges to the length over 2 plus 1. And that's sort of the length plus the Euler characteristic actually. But Mark Meckers, analyst, showed that we can define, if we've got a compact space, we can define the magnitude of the compact space just to be the supremum of the magnitude of all the finite subsets. So that should be finite subsets in there. And if we've got a subset of Euclidean space like we have here, and we've got some sequence of finite metric spaces converging in the Hausdorff topology, then the magnitude of the sequence converges to that should be the magnitude of x. So we can approximate compact metric spaces by finite spaces and work out the magnitude. And this then extends magnitude to a much bigger class of spaces, sort of compact infinite spaces. And this has a lot of interesting structure in its own right. So for instance, we look at the magnitude function, what happens to our metric space as we get bigger, then the growth rate of that is the Minkowski dimension, it turns out. So we're recovering the fractal dimension. So I didn't have to say these spaces particularly nice. You can take the Sierpinski gasket or whatever, your favorite fractal, that will have a magnitude, and the growth rate does in fact recover the fractal dimension. Here, I mean, that's the growth rate here is just going to depend on this linear term, and that's because we've got a line and it's one dimensional. So then Tony Carberry, Antonio Barcello, and then some further calculations by me worked out what the magnitude was for various odd dimensional balls. So for instance, so typically this is really hard to calculate. I mean, we know very few calculations of the magnitude exactly, but if we take the 3-dimensional ball, for instance, you can show that it's this polynomial. Now that takes quite a serious amount of analysis actually to work this out. But I showed in general, if we have an odd dimensional ball, it turns out it's a rational function. That r should be a t, by the way, sorry. So that, I'm thinking of r as being the radius. So that should be the T. So and so of course the growth rate here is 3. It's a cubic. So so that's obviously related to the growth rate. The leading term is of order 3, which is the dimension of the ball. But in general, a kind of quite a serious amount of analysis and various other things, I sort of was able to show that for odd dimensional balls, 3-dimensional balls, what you get is a ratio of determinant of Bessel polynomials. So you get some beautiful special functions cropping up here. But bizarrely, I mean, an exact formula for odd even dimensional balls, even the 2-dimensional disk, we don't know what it is. It's quite bizarre that we know one but not the other. And then some analysts, Goffing, Gimpelane and Loka, looked in general at n-dimensional Riemann manifolds with boundary, and they showed that as you scale up your Riemannian manifold, so the leading order term up to some constants here, which we don't need to say, the leading order term is always the volume. So that's what you kind of saw here, was the leading order term was the length of the line. And the subleading term, if we've got a manifold with boundary, is the volume of the boundary essentially. So the magnitude is encoding this geometric information for infinite metric spaces, despite its humble beginnings. There's this thing involving enriched category theory and Euler characteristics. So that's sort of this really nice thing about magnitude. Okay, so that was a whistle-stop tour of magnitude. Now I just want to, so I'm sort of running out of time, so I just want to mention just one bit before finishing this whistle-stop tour. I just want to go back finally and very briefly to just say a little bit about the category theory and give you another example of where this enriched category theory picture helps. So there's a thing in category theory called the enriched Isbell completion. So we talked about the Uneda embedding. A category embeds in these sort of scalar valued functors, and there's a relation between these, the so-called Isbell adjunction. So you get maps between them, and we can look at things which live, pairs of things inside the thing on the left hand side here and on the right hand side, which get mapped to each other by this adjunction. So I realize I'm going through this quite quickly because I'm essentially running out of time. But if we consider the pairs of things, one in the left hand side, one in the right hand side, such that the F here gets sent to the G and the G gets sent to the F, then that gives us a notion of sort of extension or a completion of our original category. And this is a sort of standard category theory construction. Now, if we do this for metric spaces, what we get is that these things can be thought of as living inside a Euclidean space. Now, let's just take a classical metric space, 3-point metric space with distance between them. And then this Isbell completion you get is this kind of complex here. And sitting inside it is this little tripod. And it turns out that this thing is a classical object for metric spaces known as the tight span, which has been rediscovered many, many times over. And this sort of drops out of the enriched category theory and gives a generalization of it for these enriched categories. So this, I just wanted to mention this because this was also looked at, although this drops out of the enriched category theory, this was also looked at by Kamaju Kunze and Ola Artafudu as well, as people in operations research and people in tropical algebra. So I realize, sorry, I just rushed that bit at the end, but I did want to mention that bit. So given you quite a broad safari there, taking in quite a bit of things. So I just hope I've shown you why this is a useful idea to think of categories as enriched categories.
Okay, thank you very much, Simon. And yeah, let's all unmute our microphones and just give him a round of applause for that lovely talk. Remarkable how we went from thinking what's the right way to think of what an algebra is and what's a representation of an algebra, just thinking about that. And then within 30 minutes, we were really, the maths just exploded, and we were talking about Riemannian geometry and Bessel polynomials and all sorts of things. And yeah, I think that's quite amazing. So any questions for Simon?
Yeah, so maybe an easy one. So why is it called tight span of X? Like,
why is it called the tight span? So it's sort of the yeah. So maybe I shouldn't have shoved this in at the end. But it's sort of the small. It's sort of the tightest metric space. So here we have three points, and we want a sort of a contractible, well, slightly better than contractible metric space in which X sits. So you sort of take contractible metric space and sort of think of it as being really, that's the tightest metric space that squeezes in between those points, is one way of thinking about it. So if you're trying to place network things on a server, or you're interested in phylogenetic trees, then if you're thinking about maybe if you've got some species and you want to think how these are related, what their genetic relationship is, you want to build some family tree, and you know what the distance between these points is, so these might be species, and you know what the difference between them is, you want to kind of come up with a something like a family tree, and it turns out that this tight span is a sort of good first approximation to doing that. So it's the tightest metric space you can do that sort of interpolates between those points.
So I've got a question. What are the open areas of research the interesting questions here that can be pushed forward? Yeah.
So there's a few there's many things here. Sorry. So for instance, kind of understanding there's lots of things in magnitude. So kind of understanding this categorification. So having these homology theories when we've got infinite metric spaces. So you can do it, but they don't seem to tie up. So this theory is very nice for finite metric spaces, but if we go to infinite metric spaces, then we can define this this magnitude homology, but it doesn't seem to be connected to the magnitude in the same way. Now we've got some beautiful formulas, for what magnitude is, but we don't seem to be seeing that in the magnitude homology. So that's one area. Another area would be what was another area? Yeah, so it turns out that this stuff is related to tropical algebra and convex analysis in various ways. So there's a whole thing about trying to get convex analysis in this classical sense into this framework, because it looks like a lot of the mathematics there is very similar. So there we're not enriching over the non-negatives, we're enriching over all real numbers. And so there's lots of interesting stuff going on there. So that's a couple of areas.
Thanks.
And yeah, sorry, maybe I should.
Okay, yeah.
It's actually connected to the generating series you had, and was somewhere. Yeah, you had a couple of signed integers there, and I was wondering, like, does this I mean, do you have like a factorization where maybe these integers are positive or something? Are they counting something? Or
so these integers, in this case, yeah. So I rushed through this somewhat, but it turns out that these are always going to be counting these kind of well, I'm not sure which bit you're asking, but they are just the ranks of certain abelian groups, so they are just counting dimensions.
Yeah, but they were assigned, like you have negatives and positives. So
right, because it's the, so what we're doing is we're taking the Euler characteristic, so we take alternating sums. Sorry, yeah.
Sorry, yeah.
So
thanks. Yeah, I get it.
Yeah.
I think there was one question earlier.
Yep.
Yeah, I wanted to ask something like how are we thinking this this by-graded homology, this by-graded homology as the enriched categories?
So the yeah, so that's a kind of complicated story. So the idea is that in order to define this bi-graded homology theory, you need some extra structure on your enriching category. So if we got V as our enriching category, then so back here, I mean, to define the original, this idea of Euler characteristic, we needed that V had some notion of size, and that was kind of encoded in this exponential function here. But in order to categorify this and come up with a homology theory, you need a functor from your V into some abelian category, and then in that abelian category is where you do the homology theory. So there's some little bit of extra structure involved for your enriched category, yeah, which allowed you to do a bit of homology theory. So
okay.
Yeah.
Okay, this was really fantastic, Simon. Very inspiring, and wow, I look forward to actually watching it again on YouTube. So I'm glad it was recorded. And as far as the African Math Seminar goes, I think I'm going to hand over to Jared now, because I guess we are taking a Christmas break now.
Yes, that's right.